Welcome. This is Xing Jin from School of Architecture and Planning, Nanjing University. I'm welcome all of you to join this foreign frontier forum. Okay, I also the associate editor of this journal. So today we have Professor Ma from University of Wollongong, Australia. Before the speech, I want to introduce our journal and Professor Ma briefly. So firstly, is about the journal. You can say the Journal of Building Design and Environment. This journal was founded in 2023. And we have 3 issues per year, and you can here see the aim and the scope of the journal, including building design and structure, indoor environmental quality, etc. And our target impact factor will be 7 before 2029, and we will have no publication fee before 2029. And we also have the WeChat account. So welcome all of you to follow and support our journal. The Honorable Editor-in-Chief of the journal is Jian Kang from University College London. He is also a very famous expert in architecture acoustics, and he is also the foreign member of Chinese Academy of Engineering. And the 2 editor-in-chiefs is Professor Li Maozhang from Huazhong University of Science and Technology, and Xiangyu Wang from East China Jiaotong University. We also have 9 associate editors, including me, and Professor Li from Guangdong University of Technology, and Professor Duan from Tongji University, and Professor Hao from Xi'an Jiaotong Liverpool University. And so we have, and you can say they are all the famous experts not only in China and also around the world. Most of the members are from China and Australia and other Western developed countries. This year we also have young editorial board members. Right now we have 47 young editorial body members. And I also welcome young scholars to join the young editorial members of our journal. Okay, and to promote the global academic exchange, our journal has launched 2 major series of academic activities this year. The first is what we are doing right now is the Frontier Forum. Actually, we have already have 6 sessions. We invite international renowned expert in the field of building and environment. And you can see here, we can see Professor Time from Australia, and also Professor Matt, also from Australia. It's the University of New South Wales. So he's very famous actually in my research area. It's in the building energy and the environment. So the second is the emerging forum. It's for the early and middle career researchers. We have launched the forum in October actually. The first session, you can see here is Professor Duan Zhenhua and Professor Cao Liu. So they are very excellent young researcher in structure, concrete structure. We have the views is more than 100,000 times. In addition, the journal has launched the Voice of Scholars interview series this year. We have invited dynamic researchers from various fields to share their insights and appearance. So far, we have 8 scholars focusing on the topics such as resilient building, net zero energy buildings, and building like innovations in building technology. Okay, next I will introduce Professor Zhenjun Ma. I just checked Professor Ma's CV online. I know Professor Ma got his bachelor and master degree from Xi'an Jiaotong University and get a PhD from Hong Kong. Right now, he's the acting director of Sustainable Building Research Center, University of Wollongong. Also the fellow of Australian Institute of Refrigeration, Air Conditioning and Heating. And also he's the associate editor of 2 international journals. You can see here it's Solar Energy and Energy for Sustainable Development. His research area including building control, building demand flexibility, and big data analysis, and low carbon heating and cooling technology. So next, let's welcome Professor Ma to give us the presentation. So, Professor Ma.
Thanks, Professor Jing, and for your very nice introduction. So can you stop sharing and I can start share my slides?
I will stop sharing and you can share your file.
Okay, great. Thank you. So are you able to see my slides?
Yes, I can. It's ready. You can.
Okay, thank you. Good afternoon, everyone. And it's my honor to be invited to give a seminar in the Decarbonisation Journal of Building Design and Environment. I know this journal for a long while. Even I haven't been really actively involved in this journal. But it's for a new journal, it always takes some time to develop, have some impact and other scientific influence. So my talk for today is really about enabling building decarbonization through energy innovation and digital intelligence. It's really from demand flexibility. So that's my team has been working in this area for a long while. And so some of you, if you haven't know the University of Wollongong, so we are in the New South Wales in Australia. So as you can see that we have 1 hour drive from Sydney International Airport. So this is our campus. So our campus, our university is around 70 years, and we have over 30,000 students, and we are really international students. We are students from 130 countries. So you can see there is some local, quite famous places, and we always welcome visitors in our region. And so this is our city, and my research group, SBRC, the Sustainable Building Research Group, is here. It's very near the sea. It's only working from 5 minutes. And so our teams, we work on a range of research activities, net zero energy buildings, distributed energy resources, and indoor air quality building control. That's all part of our research activities. And you can also see we have set a range of living labs. So living labs to support our student project and research activities. And we also have a range of research facilities, for the microgrid test platform and building inside test facility and outside test cells. That's all the facility to support our research here. So for today's my presentation, so I will start with some overview for the what's energy in buildings and what's key activities in Australia and beyond. And then I will give you an overview of the research activities my team is doing on the accelerating energy innovation for building decarbonization and digital intelligence and demand flexibility for building decarbonization. So this is a journey for the net zero efforts from from Australia and also in our team. In the 19th centuries, further we have bio and fossil fuels is really used for the heating and lighting. And then we also have discovered the PV effects by the leading researchers. So then come to the later part of the 20s. So solar thermal is becoming common, and for the remote area power system for off-grid homes is also becoming popular. And at that time, the batteries and the diesel backup is also used, and the PV panels is increasingly used. And the small-scale wind turbine is used, but that is not very competitive from cost perspective. Then come to the 2000 years. So in Australia, so we have first 6-star building. That is a council house building in Victoria, in Melbourne. So in this building, they use a range of high performance technologies, including the phase change material in the building for storage and load shifting and load shaving. And also the digital building management system is also used in this building. And many of you may know in the 2002 and in the United States, they started for the solar decathlon international competition for the solar decathlon. And come to the 2010 and large scale roll out for the roof solar panels, and also net zero energy buildings, and that's becoming very popular. So in Australia, we have first carbon neutral building is developed. And at that time, also demand response management enabled devices is becoming popular in homes and office buildings. And from government policy perspective, the code of practice for energy efficiency is also in place. So, well, what's happening for today? So in Australia, so we have 38% of homes, they already installed solar panels. That is around 4.3 million homes. And also, so you can imagine, so these solar panels will generate significant amounts of power during the daytime. And so we need a high interaction with the grid system, because in the daytime, for the homes, they really don't need a lot of consumption. And most of generation will be imported to the power grid system. So there come a lot of issues from the stability of grid operations. And from the 2015, so around 3 million or 3,000 megawatt hour battery storage was installed, especially from this year. So Australian government, they put a lot of support to install the battery storage system behind the meters. And so some of you work on the advanced controls. For instance, MPC, so model predictive control, is also being tested in the buildings, and AI technologies are also started using the buildings. And lots of activities happening on the grid connected battery system, and EV cars is also close to the commercialization, and you can see a lot of EV car, and from the vehicle to buildings, vehicle to grid, and grid to buildings. That's all the topics currently under investigation. So many of you know that building decarbonization is not only for the energy efficiency, so we rely on a lot of technologies. So renewable technologies and electrification is also equally important. So So all in the we need to look at all the different ways to reduce carbon emission from buildings. So that's it from this study, really from the International Renewable Energy Agency. So they identified 6 components for net zero transition. And so this is where some introduction for the work my team has been doing over the last couple of years, on how we can help translate our research activity to help reduce carbon emission from buildings. So one of the key technologies we studied is the intensified solar collectors. So you can see that this facade, we installed intensified solar collectors. And in principle, in this facade perforated panels, you can see a lot of small holes. So these small holes, actually, if you look at this figure here, so they have a small fan in operation. If the small fan is in operation, so the pressure inside of these channels will be negative. So this is perforated sheet, this sheet here. So the outdoor air will flow through these small holes. And because you have strong solar radiation in the facade, so the air will be heated up and come to if under the very good solar radiation and the sunny days, so this can reach the 25 or even higher hot air. So this hot air can be directly into the indoor space for space heating in winter. So you can imagine, so this is the technology, it really is based on the design principles. So the power consumption from fan is very small. So this is nearly a passive application of the using advanced design to facilitate heating in the buildings. So we also did a range of measurements for this facade, and you can see we installed a lot of thermocouples and flow meters and to quantify what's the benefit. And we also try to look at, for the diameters for the holes, or you can open I'm opening in the big opening in the bottom. So which is the best options? We run a different scenario to say what's the optimal configuration and the design principle to support this kind of facade technology. And so this is some measurements we did. And when we look at the different air flow rates, so you can see the different outlet temperature from the intensified solar collectors. And in principle, you have a smaller air flow rate, you have a higher temperature. You can see in the good weather condition, the out air temperature can reach 50 degrees C. So that's very useful in the winter time for space heating. So if you look at the right side figure, so you can see that we compared to different type of panels. One is a corrugated panel, and then another blunt plate panel. So we look at what's the heat loss from the panels. One is the convective heat loss and the radiative heat loss and useful energy. So from this is the really a way is how to make sure you have a very good design to make building more efficient. So this is the one technology, and we also look at options to integrate thermal storage. So in this case, so it's combined with phase change materials. So you can either install in the internal layer or outside is next to the perforated panels. And also you have the one without using any thermal storage materials. And which one can provide better results or outcomes. And this is some simulation work based on for these 3 scenarios, and so that you can see from the indoor air temperature perspective. And the one is, so this is the winter scenario. We need a higher indoor air temperature. And you can see that when you combine the transfied solar collector with thermal storage using phase change material, they can show the higher indoor air temperature. And its temperature seems very similar when you compare with the transfied solar collector Olin, but both of them much higher than the baseline scenario. And the benefit of phase change material is really highly rely on the way you can put the material and how much material you will be using. And that's a lot of factors. So if you look at the right side figure, so this is really tell us the average room temperature when the fan was off, so without fan. So you can see for the different days. And if you have the transpired solar collector and thermal storage using phase change materials, you can have in principle, you have a higher average temperature compared to the other case. So this is really demonstrates the value of transpired solar collector and phase change material. But they are behind the technology, there are lots of design issues and design optimization. So the second technology is what we developed is photovoltaic thermal system, is PVT. So in our case, we developed the air-based system. So why we developed air-based system? So in Australia, you can see a lot of roof structure is like this way. It's still in a steel roof structure. So the idea is and we can retrofit the existing buildings by using this existing roof structure. So for instance, in this roof structure, you have lots of valleys here. So the idea is just put a layer of thin film PV panel. You have one layer of PV panels, so I can use these valleys and the channels for the air channel. So this is from a very low cost retrofit solution. So this PVT of course in the summer daytime, you have a PV generation and you have a hot air generation. So many of you may know is when the temperature of solar panels is increased, and the efficiency for electricity generation will be decreased. So if you have air passing through below the panels, so they can reduce the temperature of the solar panels and can slightly increase the electricity generation efficiency. And on the other hand, you have hot air. So in the summertime, in the daytime, in the hot summer days, so this hot air, either you can directly discharge to the outside, or you have other solar-driven air conditioning system. For instance, for the basic wheel or other thermal-driven air conditioning, that will be a solution. But in the winter time, you can imagine, so this hot air is very useful. You can directly use it for the indoor space heating. So that's really in the daytime operation. But come to the nighttime operation. So in the nighttime, so you have a sky radiation. So which means when the air passes through this channel, and because of sky radiation, so temperature of the inlet air can be reduced by 5 degrees up to 5 degrees C. So this you can use for the nighttime pre-cooling for the inner operations. So we also look at how to increase the performance and of these kind of panels. For instance, we look at the combination from PVT and the solar air heater together. It really tries to increase outlet air temperature from the PVT system. We also look at using the heat pipes to increase the outlet air temperature. So to test the performance of this kind of technology, so we developed such kind of test rig. So you can see this test rig, and we have you can change the orientation. So to change the sun in the daytime, in the morning you can face east, and in the late time you can face west side. they really trap the solar radiation. And you can also change the slope of the panels, because slope of the panels is also a factor to influence the efficiency of PVT system. You can also change the vary the air flow rate to look at to test the performance of such technology. And so to look at the integrated performance with thermal storage, so you can see we also install the thermal storage system to store the hot air from the PVT system. So in this case, we use the salt hydrate material and put in the this in the brick style. So put in the channel to measure to evaluate the performance of such integrated system. So for instance, this is some measurement data from our system. So we look at under the different air flow rate, what will be the thermal generation and what is the electricity generation. So in principle, electricity generation, you cannot say significant improvement, because for the thin film solar panels, efficiency is always around 10%. But if you can improve 1%, that's a significant improvement. And it's really for the different air flow rate, it highly impacts the thermal generation. So that is from the air flow rate perspective. And you can also say from the slope of the panels, you can have different slopes and you have different efficiency. So this really depends on the climate conditions and location for the PV panel is installed. And so we also look at the combined PVT system and thermal storage in the integrated with the HVAC technologies. So for instance, so this is one example we developed. So we have a PVT collectors and we have a PCM thermal storage and integrated with the air handling unit. So that is integrated with the heat pump unit. And so this system can provide different options. So for instance, in the winter time, you can directly supply hot air to the buildings, or you can preheat the air, then using the air handling unit to further heat up the air. Or you can store, you can have a heat is charged into the PCM storage and then use later when needed. So we installed this system in this net zero energy building. So that is underneath the hubs. We installed this thermal storage, and PVT is on the rooftop. So this part is our PVT system. And in this system, you can see that this is our air-based PCM thermal storage. We installed underneath of the building, and this is our control infrastructure. So we developed to optimize operation for the PVT and air conditioning and the thermal storage is through this interface we developed. So here is an example. So that for the hybrid model predictive control we developed for this system. So we use two different layers or levels. So one is high level controller. Is really to determine the operation mode of the HVAC system. For the using the air handling unit for heating or cooling, or using the PVT for preheating. So this is based on the time interval for 1 hour. Then we have a number of low level MPC is to optimize the local level air, for the such as for the PVT air flow rate, for the charging and discharge of PCM storage, and all this will be communicated from the desk controller, and we use LG air conditioning. So that's from desk controller and the C-bus and the weather station. So that is really a real demonstration the performance of air conditioning system and also high performance advanced control strategies. In this case, we use MPC. And this is some measurement data. So you can see in principle, so the in the indoor air temperature is in the required threshold, that's the up limit and low limit for the thermal comfort. And so, for instance, this time we use the PVT for pre-cooling, and here we use the PCM for discharge. And so this is one example. So we also have another example is installed in another. So in the previous one we use air-based system, but in this case we use the liquid-based thermal storage. That's the two thermal storage system. We still use base change material integrated with the heat pumps, and so we also use the energy recovery ventilation to try to reduce the power consumption from buildings. And so this air conditioning unit is installed in another building, is in the other house we developed. And so you can see that's the PV panels and PVT system installed in the building. And this is for the thermal storage we designed. So in this case, we use the liquid-based system, and you can see this is the PCM tubes. So we installed many 196 PCM tubes. So this frame installed in this storage tank. So the liquid water is passing through the PCM for the charging and discharge. So in total, we have 2 different tanks. So in total, we installed 338 tubes. So that's one is 196. So for both storage tank, they have a storage capacity is 35 kilowatts. It's really for the load shifting purpose. And you can see that this is the 2 PCM tanks we installed in the building and integrate with a heat pump unit to provide heating and cooling for the building. And so this is for the rear building installation. So we also have an enthalpy heat recovery ventilator put in the cage of the building and installed on the roof of the house. And so you can see that that's our layout for the air conditioning units is where for the ducting system and PCM thermal storage and heat pump unit is installed. And so in the design stage, especially for the PCM tank, we look at different options, for the diameters of the tubes and the distance and to the diameter of the tubes, and also look at different PCM types and look at what will be the inlet water temperature. So that's collectively is a complicated design optimization. So for this system, we also developed MPC, so model predictive control, to control the lights, control the HVAC, and also have PVT and a monitoring system, and we also have a storage system. And we have a 6 kilowatt electrical storage. And the purpose of the MPC is to control the real-time power below the 80 kilowatts. So that's because that's a very hard target. And you can see so that's for the red dashed line is before the implementation of the controller, and this curve is the yellow curve is after implementation of demand response programs. And but even implement the demand response program, and we shift the demand time, but the total power is still above the limit. And then we implemented this MPC controller, and this is our target. You can see we didn't reach over exceed the limit, and but in this time we increased the power consumption and peak demand time, we reduced the power consumption because of the predictive function of the MPC. So another technology is we developed is the air-to-air membrane enthalpy exchangers. And in the HVAC system, so the ventilation consumes a lot of power. And we look at the ways and to achieve enthalpy recovery ventilation. So we look at this kind of configuration, and this is really membrane-driven technology. So our work is really to look at MOF. Many of you, if you work on the material side, you know that MOF is a metal organic frameworks. So we have coatings on the different coating materials on the membrane to look at how they can improve the heat transfer effectiveness. So this is the two different types of coating material. Is the MOF we used, and we also look at for the air, this is supply side, and this is the exhaust side. We look at the coating material on this side or on the other side. And so we have an experimental setup. You can see that we use this acrylic frame and used to prepare the composite membrane. So the membrane. So this is the key test section for the membrane technologies. And then we set up this kind of experimental setup. So you can see these are the environmental chambers to control the inlet temperature and humidity. We have two of them, and to control two different streams of the air. So this is the membrane enthalpy heat exchanger. So that's the inside is this really for this part. And we have vacuum pipe, and this is a flow meter to measure the performance of such kind of enthalpy exchangers. And this is some measurement data. You can see that so when we are under the different test conditions, so the red one is the membrane. We didn't use any coating material, and for the blank and the blue one, they use two different coating materials. One is ZIP and another is developed by the Hong Kong UST. So you can see that through the coating this special layer of MOF, the moisture diffusivity of the material membrane is increased a lot. So one of the key performance indicators, you look at the water contact angle. So you can see that from the advancing and the receding measurements. So once we have the coating materials, so they really improve the heat transfer effectiveness. So this is really from energy innovation perspective. And second part, I will give a quick overview on the work we did for the demand flexibility and digital intelligence. It really the demand flexibility and the digital intelligence, they are interconnected. And you can see that in the past, so the power plant or electricity grid provided we always have a few very large power plants. But currently, you can see that in the future, we have many small-scale power producers. Have off-site solar panels, remote area solar panels. We have grid-side system. And in the past, that all the centralized, mostly for the national level, you have a number of large power plants. But in the future, you will see we have centralized, but they all have smaller ones. They don't have very clear boundaries between each of them. And also that's based on large power lines, but in the future, all the distributed energy lines. And in the past, we always look at top-down method is only one-way communication. But in the future, that's the two-way communication. That is give on the one side, give a lot of opportunities to optimize buildings and the grid at the same time. But on the other hand, it increase the complexity for optimization. Because in the two ways optimization, you have a range of increased factors and complexities for the optimization question of problems. So we have been working on a number of projects. So one is we call the digital infrastructure for flexible and demand. So we have a number of research organizations and a number of industry partners. It's looking to build up digital infrastructure for flexible demand. So the overall objective, from the end user perspective, we try to reduce the cost of their operational cost. Then from the system integrated perspective, we try to enable existing supply chain and make sure it's very smooth and is easier. Then from the electricity retailer perspective, they try to reduce the flexible demand delivery risk and also try to reduce their transaction cost. But then from the data analytics providers, they try to reduce cost for their service provided, and from the government regulator perspective, they try to enable policy interventions. So this is really, you can see the integrated solution with multiple stakeholders to be involved. So with such kind of digital infrastructure can make the transaction and it's easier, and also will be make the end users to increase their confidence to participate in the demand side management, and also whether it will be financially visible and or cost effective. So this is the main purpose we try to build up such kind of digital infrastructure. And because in the maybe in the office and residential buildings, we have a range of flexible demand assets. So for instance, you have electrical hot water system in the home, and you have chilled water system, and you have other air conditioning units. That's all the flexible load, so which means they can change their demand, they can change their consumption. And so some buildings, so we have thermal storage, and most buildings we will have water tank, or some buildings, like the one I mentioned very beginning, they have PCM thermal storage. And more importantly, all the building envelope have a thermal storage capacity. And for the large scale buildings, they have standby generators, and they also have renewable generators, and for the stationary batteries and also EV batteries. That's all the flexible demand assets we can use in our building to increase demand flexibility and reduce the operational cost. So this is some examples. We worked together with our partners, to look at how to quantify the demand flexibility. So we introduced concept we call it demand response plan, either the all increase or decrease the power, because sometimes we need to increase the power consumption and sometimes we need to decrease the power consumption. And so for all the flexible demand assets, we look at different, for all the flexible demand assets, we look at what's the demand flexible capacity, so which means how much demand flexibility they can provide by using this kind of device. And also we look at the duration of the response, so how long they can provide the demand flexibility. And we also look at the activation time delays. And for the assets, they have a storage. We can also look at the storage volume and round trip efficiency or minimal time between events, for the charging and discharging. That's all the factors we are considering. So the idea is that we make this demand flexibility quantification online, and
recording in progress
flexibility. So that's our major purpose, to build up this digital infrastructure. And so we tested some buildings. For instance, this is our office building. We integrated or onboarded to this platform, and we run a range of tests in this through the air conditioning units and different demand flexibility assets in the building. So this is for the BMS system, and they monitor and collect all the data from the building. And you can see that this is some real trials in the building. So this is for the load shaving test. And you can see that in this time, we increase the set point for the air conditioning, and for the different office area of the rooms, you can see they cannot really reach the set point exactly. So for instance, the set point is 25.5 degrees C. And so many to these three thermal rooms, they didn't really reach the set point. So this is in the real building, it's real challenge for to set up a reasonable baseline or reliable baseline conditions. And if you look at the right side figure, so this is when we have a demand response. So this is the real measured power consumption. And so we use three different ways to determine the baseline, which means we estimate without demand response program and what will be happening for the building. So you can see we can use the experimental baselines, so similar day method and the regression method, they all come up with different baselines. So this makes it very extremely difficult and challenging to determine how much savings from the demand response test. So this is another example for the load shifting. So we decrease set point before the peak demand time, and then increase set point time, and then increase set point to reduce power. So you can see can simulate the grid operations and provide signal to the buildings to control the power. So this is the real tool for the two-way communication and support the demand side management. So for instance, this is a digital twin model we developed. We used the Energy Plus for the building envelope and using Dimola for the HVAC. So that's coupled through the Python program, through the OpenDSS, and we also have a firmware machine interface. So all the controllers can be implemented and tested through this building. And I think that's quick introduction and for my presentation. So lastly, we are organizing an international conference next year in my university. That will be in October 7 or 9. And 2026 is on digital intelligence for energy systems. And you are very welcome to join the conference. So we have some key dates. Ambassador submission deadline is March 1st, 2026. And so that we have all the three journals. We will publish our select paper. We are published in these three journals. All the conference paper we are published in the book series in the Spring Nature. And so this conference we are jointly organized. We are held together. We have an Annex 96 workshop. That is pretty much for my talk. And thank you. And any questions?
Okay. Thank you, Professor Ma, for your excellent presentation. So very interesting, very impressive. Actually,
yeah,
Professor Ma introduced two parts. One is about the three kinds of energy saving technology or system. The second part is about the building decarbonization. So for the audience in the room, do you have questions? You can turn on your microphone and communicate with Professor Ma directly. Oh, here we okay. Anyone? So firstly, I have a question for Professor Ma. Actually, it's for the first part. It's very impressive for technology, especially for I remember it's PVT, right?
Yeah.
Because I think I am from the School of Architecture and Urban Planning, so it's not from like mechanical engineering or civil engineering. So my question is, you only have not only have simulation and experiment, but actually you use this technology or system to a real house. So can you introduce about the house? So what I mean is because usually we have done a lot of research, but it's very difficult for us to use the technology in a real building. So what kind of this building? It's a residential building or a commercial building, or why the owner want to? So how you can to they they have the willing to use your technology actually.
I think that's thanks. Yeah, that's a great question, and I think that the implementation is in the residential buildings and also in the commercial office buildings. And we did lots of trials, and I think the real challenge is not the technology itself. And the idea is from the retrofit technology or retrofit of existing buildings. So we really want to use the hot air produced by the PVT for space heating in the winter time. So one of the challenges we faced is in the real implementation, and you don't have space to install the additional ducting system to direct air into the indoor space.
Yes.
And so this technology is the idea is from the existing buildings, but it's more useful for the new buildings because in the HVAC design, the ducting system is it use a lot of space and the design is quite complicated. If for the existing building retrofits, it's very hard to find a space to install additional ducting system. But it's good technology. There are lots of research on the water-based or liquid-based system. So we use air-based because we want to reduce the initial investment cost and use a current roof structure. But compared to the liquid-based system, of course, this the overall efficiency of this one is lower than the water-based, because water-based you can increase heat transfer. There are a range of technologies. So to be honest, any technology translate from research to the real product, they have a long journey and long way, to refine the product.
Okay.
But we are still trying our best to make it, to be practical and to reduce the challenge and issues in real-time operations.
Okay, thank you. And can you say the question from the chat or the button? You can click.
Yes. So the Q1 is an innovation and intelligent retrofit for building decarbonization often involve high initial investment. Yes. So how can a sustainable business roof be built through the approach such an intelligent operation and maintenance to reduce the cost? I think that's a real very good question. Excellent question is because that's always owners. They are interested in investment, for investing technologies with a smaller payback period. So for instance, whether we work with many end users, if the payback period is less than 3 years, they always have an interest to test this technology. If the payback period is over 3 years, so they always they will ask a range of questions. So I think a sustainable business model is we usually we started with case studies and demonstration and showcase. So for instance, in our building here, so we have 2 net zero energy buildings, smaller hubs. And every year, we welcome maybe more than 2,000 visitors. They come to the hubs for our building to look at the technologies we used, and they also look at, want to taste the product. That is some way our team here is working. So we have the demonstration showcase first, and that increase the confidence and identify the potential operational issues. And but bear in mind, so once if the building is there, if technology system is already there, if the implementation of intelligent operation is a low cost, and it really install some additional IoT device, low cost device sensory technology, and you didn't really need a lot of investment. Investment is always from the install additional system. For instance, if you want to install the battery or PV panel, that it always costs a lot of money. But if this technology already there, and the implement, whether if you want to use intelligent operation, I think that's the minimal cost investment. But one of the challenge is how to increase the confidence of end users, because end users always welcome the reliable solutions. So sometimes too sophisticated solutions, and whether in the very beginning maybe you test performance is perfect, but after 1 year or 2 years operations, that's maybe the performance will be different. So this is really a real challenge for the digital intelligence or AI machine learning method. So you need continuous learning and training the models and method. I hope I answered the first question. So second question, compare with the traditional black box models. So what unique advantage are physics informed? Using physics practical baseline model. Okay, so I think the key that maybe that there are lots of research happening on the PIN is physics informed neural networks. I think the benefit is they try to reduce the computational cost is one way. And on the other hand, and I mentioned machine learning models, most of them are data-driven models, highly rely on the data-driven. So the merit of the physics-informed models, they have physical components. So for instance, if you look at the most physics-informed machine learning models, they use the RC model, the resistance capacity model, to build some physical components. It's really to make sure on the extreme certain conditions. So this model can still provide a reasonable prediction, not far away from the real case. So that's the way why the physics-informed method is these days they are very, very popular. And but also compared to the physics-based models, blank box and white box models. So this model they increase the efficiency. So it's really for the online applications, and we need to try to address computational cost, and we also try to increase the reliability of the method and models. So physics informed is a trade-off between it's not a perfect method, but it's a trade-off between the different objectives. I hope I also answered this question.
Yeah. Thank you for your explanation for these two questions, and also for my questions. And any other questions? Okay. If we don't have a question, I think the time right now is in more than 1 hour. I think it's time to close this Frontier Forum. So thank you again, Professor Ma, and thank you all the audience to this forum. And
yeah.
Okay, thank you very much.
Thank you. Yeah, see you. Thank you. Bye.
See you. Bye bye.